Let's get started. So for the last talk of the student session, got Ian Mertz. So I guess just take it away, bud.
All right. So yeah, thank you to everyone for coming, and thank you to the organizers for allowing me to speak at this venue. So I am going to talk about a line of work that I worked on throughout my PhD and continue to work on that I really like. And I'm going to give kind of a student's eye view of it, aka the order in which it happened and not the order in which really makes sense. So it's only in retrospect, of course, with Tony that we could piece it together and make something cohesive. And let me just start at the beginning, which is me coming to Toronto. So I did it was the visit times, and I visited UCLA for a few days. And then I was super bummed to fly back from UCLA to the East Coast, Princeton, because it was a drop of whatever, 10 degrees and the weather got visibly murkier. And then when I went to Toronto, the same thing happened with respect to the East Coast. I showed up and it was pouring rain. It was miserably cold. And my first thought off the plane was, well, at least they're giving me a free visit. And it took 8 hours to convince me to come to University of Toronto from that. And it basically happened because of 3 conversations. The first was just talking to Steve Cook, realizing he was research active. That was not the conversation. It was about like boats and the opera and other stuff that he likes. It was going to the bar with Robert Robert, my co-organizer, who was very social, extremely so. And most of all, of course, it was talking to Tony, who is kind of the best of all of these worlds, who is obviously extremely social and fun, and who has a great knack for research and makes those conversations so exciting. So I felt like Toronto, after that, I really felt like Toronto was the right place to be. And in retrospect, of course, it was the right place to be. So when I got there, I was co-advised by Steve and Tony, and there's a rite of passage for everyone who works with Steve, which is you have to work on the tree evaluation problem. So yes, the tree evaluation problem, this is Steve's pet problem, and that he's been really working seriously on since, I think, 2009 or so. It looks as the following. You have a full binary tree given to you as input, where at each of the leaves, you have an element, say, 1, x2, x3, x4, and TP is characterized by an alphabet size k, so each of these things is an element in the alphabet size k. And then in the internal nodes, you're actually given an entire function, which takes in 2 inputs over k and spits out an output over k. And of course, the way you evaluate this thing is from the bottom up. Those aren't matched. There we go. So the tree has height h, which is the other parameter for TP, and you evaluate this in a natural way. You start with your leaves, you feed them into the function, labeling the node right above them. You take the output, you go up and up and up, and that's what you get. And Steve and Tony and Jeff Edmonds and a couple of other people were working on showing that this thing is so the conjecture was that TEP is in polytime, but not in log space. So showing it's in polytime is easy. You kind of do the algorithm I just outlined, but the whole goal was to show that it's not in log space. And Steve had an even more ambitious conjecture, which is that he said that TEP requires space well, let's just say it this way. It requires space like h times log k, which if you want to work out the parameters, this is more than log space. But the intuition is simple. Let's say I want to compute the top node of this tree. If I want to do that, I'm going to have to compute both of the children. So let's say I just give you one of them for free. You do all your work on this left side and you just get an answer. Now you have to compute the right node in order to get this. And what do you have? Well, you have a TEP instance of height 1 less, and you're remembering some element for here. So now let's do the same thing. You compute the left over here, now you compute the right, and you work your way down. And the idea is you have to remember like h minus 1 different elements, each of which requires log k bits. And that was the conjecture, and it was proved for many natural restrictions. Of course, I'm talking about space here, but the whole discussion was with respect to branching programs. So where you can impose nice conditions on them. And it was proven for many special cases. And what ended up coming out of it was there was this one problem that Jeff phrased really nicely, which was called the ZF problem. This is my first time encountering the pronunciation Z as well. I'm from the US. So the ZF problem is kind of exactly as, it's like exactly what I just outlined. The idea is you're given an input X and some long string Z, and you have a Turing machine where the work tape already has Z written on it, and you want to compute F on X, and at the end output the answer to F with Z still written down there. And the conjecture is the space of this is equal to like the space required to compute F plus the size of your string Z. And the reason why we needed to study this problem is because in the argument I just outlined, well, you're remembering all these values going down the tree, but there's nothing that says you have to, save that space and not use it for anything else. It's just, it should be obvious that you can't do anything with this because it's completely irrelevant. And so I, of course, bashed my head against the wall for most of my masters, and it was hard. In fact, Jeff Edmonds at one point made a little quip, which is that if I could make pretty much any progress, if I could solve this, I could immediately have my PhD. Now, Jeff was not my advisor and is not at University of Toronto. So he is in no position to say this. And when I realized this fact, I moved on to a different problem. But to give a sneak preview of what's to come, this prefigured the kind of work, even though I pivoted from here on out, this prefigured a really interesting line of work called composition theorems, which is essentially what I want to talk about today. So there's a lot of different ways to think about composition theorems. Here's one that I like. Let's say you have a task that you think is hard. So, we try and come up with hard functions all the time. So we go into our a big bag of hard functions and we come up with this one. And it's a natural hard problem in the sense that, it's phrased as some nice task. But one of the main reasons we think it's hard is because if you actually look inside F, there's like a first step you have to do, and then a second step, and then a third step, and all the way down. Big. And this is one reason that we think it's hard with respect to your favorite measure of complexity. But the challenge that you're facing is that, well, an algorithm may not do 1, 2, 3 all the way down. That's the obvious way, but it may actually do some other stuff that makes a whole chunk of this become easy, or solves it at one time. And this is what we don't want when we're designing our hard functions. We want to make it so that algorithms really do have to go through this long process. So one intuition is, why not just build F in exactly this way? Why don't I just come up with steps 1, 2, 3 up to big, and I will make them as completely uncorrelated and distinct as possible, such that there should be nothing that you can do to save time at by doing multiple of them at once, because they're just totally unrelated. And this is sort of the intuition behind this TEP thing, where all these nodes, I'm going to give a function that ensures that you can't rely on the correlations between the functions inside the tree and some such things. So then your task essentially boils down to the following. Let's say you've got a complexity measure of interest, S, and you have a way of combining tasks. So here I wrote it that you have to do them in order. Over there, you could think of maybe doing them in parallel. Anyway, you have this list of tasks, and you have a way of combining them. This is composition symbol circle. And what you want to show is that for pretty much all functions f and g, pretty much all, I'm hiding some stuff under the rug, and your complexity measure s that you care about, this thing is roughly the complexity of f plus the complexity of g. And if you get this, then this gives you a recipe for cooking up hard functions f, which is you just, we don't know super hard functions f and g, but we know ones that say, take exactly logarithmic space and we combine them over and over and over again. And eventually we end up with something bigger that requires larger complexity. So, all right, perfect. Let's see this in practice in a field that is not space and is in fact what I started working on after I left this behind. And it's basically just TEP with a change of parameters. So I think this was originally called the iterated multiplexer problem. And it's now it's parameterized by like height and fan-in. And it's the exact same picture, but instead of having an alphabet size, I have a different fan-in. Okay, nothing going on there. So I still have an entire function labeling it at the tree, but now let's say everything is just binary, 0, 1 inputs. And now, instead of taking 2 inputs and spitting out 1, it takes in D inputs and spits out 1. And again, I do this all the way down. I'm going to draw this.
These are all bits now?
Yeah. So these are actually like, you can think of them as D-dimensional, but yeah. Yes, Newton.
Can't this be coded using a larger alphabet in the sense that?
I guess this version, you can sort of cover this version by doing the individual bits of it. The other way around is not clear. I mean, these are very closely related problems that just went by different names, which of course was enough to throw me off as a graduate student, because when Tony showed me this problem, I went, oh, thank God, I can start working on TEP. Yeah, I was a very golden graduate student. So this, it was proposed back in the 90s, so a while before this TEP problem came up. And the goal here was to separate P from a different class, which is NC1, which is the set of all Boolean formulas. And this is equivalent to the set of all Boolean formulas of logarithmic depth. And so we were thinking of getting around logarithmic space by a composition argument. Here, we're doing the same thing with depth. And it relies on a conjecture that looks very much like this ZF problem. And this is well known, and it's called the KRW conjecture, which says that, and I'm going to phrase it in, I'll phrase it as Boolean formulas. It's that the formula complexity, or the leaf complexity, however you want to write it, of F composed with G, and composition is in exactly this sense that I write here, where you take F and then you feed in a bunch of copies of other functions, let's say even just the same function G. This complexity is roughly the complexity of F plus the complexity of G. Plus, right? It's log depth we're talking about. This isn't lifting. This is fine, right? Oh, sorry, you're right. I knew I was doing something wrong. This should be the depth. There we go. Yes, good. Conjectured to be.
It's almost the same if you have L in product.
Oh, sure. But that would be historically inaccurate. So.
Okay.
Now this is, for the complexity people, everyone sees formula depth and immediately goes, okay, communication complexity. And we're not going to go into communication complexity today, but Suffice it to say that one reason we can talk about this is that it is related to this field communication complexity, where we do think quite a bit about composition already. So for example, everyone's favorite hard function, set disjointness, is a composed problem. It's a function that looks like an OR of a bunch of ands on 2 bits. And this function is known to be hard. So, very basic function, but the hardness comes in immediately. And there are other examples of functions which are composed functions. And the other big area that came up in the last 20 years or so that has to do with composition in this realm is that of lifting theorems, which is what I actually worked on. So can anyone see back here? No. So lifting theorems have a similar sort of structure. And again, I don't want to go into it, but the idea is if we can't prove this for all f and g, let's prove it in a setting where we can do it. So it's f composed with a specific fixed function g, which we picked to be kind of maximally hard. And instead of studying the connections between depth and depth, it's depth and some weaker measure of complexity. And there's all these reasons why it's slightly different from KRW. But the important thing is that in studying this is just to write it here. If you recognize this, then you recognize it. If you don't, then that's fine. But while the goals here are slightly different, when we study this sort of question, which has a huge line of works behind it, we are studying, in part, techniques that may one day converge in KRW. And so what Tony and I worked on throughout the last couple of years of my PhD, Tony, is understanding the what is essentially going on in a statement like this and trying to get to the depths of like what mathematical objects are involved here. And in the future, in fact, this I'll just say, combinatorics, and in particular the sunflower lemma, which has seen a lot of recent developments in the past couple of years and a lot of recent applications. And these two things are now known to be very intimately connected. And what I hope to do in the future is to connect these sorts of arguments to KRW as well. And so I really wanted to understand what was going on because I want to eventually make progress on hard problems like these. And then I'll just say that there was a twist. So I ended up back here, actually. James Cook came to a seminar or a workshop much like this one about his dad's work with an amazing idea about why this should just not be true. And so we spent some time on it and we found out, in fact, that this is not true. We found out that TEP is actually in lower space than Steve conjectured. It was h over log h times log k, not the biggest quantitative improvement, but really had to use all kinds of techniques, and in particular showed that this is not true. So this shows that this is a finicky question, this composition one. Somehow we've been working for decades now on showing that when it comes to formulas and such and depth, composition works like a dream. And then out of nowhere, we find out that if you move from NC1 up to L, it doesn't work the way that we want it to anymore. So this whole question of what you can and can't do with composition, I think is eternally fascinating. And Tony, of course, walked me through this my whole way. And I'll end with saying exactly how she helped me at the end. This is all a nice retrospective on how these things work together. Again, I was not so attuned to these questions, and at the time I didn't realize that Multiplexer and TEP were really talking about the same things. I focused in on lifting. And so when it came time to write a thesis and a research statement, here's my first draft of my research statement. I said, quote, I am particularly drawn to problems where the mathematical objects in question are very basic, and yet with a bit of cleverness, they can yield results which are surprising but also accessible. And to translate that, I can't do hard math, so I only do easy math. Tony, of course, saved my career by vetoing this. And in retrospect, I can see why I thought these things might be just totally unrelated, because to me, Tony works on literally everything. And if Tony worked on TEP and lifting theorems, then Tony worked on TEP and lifting theorems. But I've grown to appreciate since wrapping up my PhD that Tony, yes, works very, very broadly, but also has a really keen sense of how these things are connected and where the hardness really comes from, and has this beautiful view of all these different objects together, and, well, knows how to push graduate students to see the same thing in their own time. So it was a fantastic PhD, and I hope to continue making progress in this on the future. So happy birthday, Tony.
Thanks, Ian. Any questions?
Is there a modified ZF conjecture?
If Z is very small, I guess, but again, you can't get it small enough that you don't get some improvements.
Do you think that number is?
Oh, that's a good question. This seems fairly unnatural, but we've had more unnatural things be the right answer before. I could still believe that this is not in log space, but it doesn't look like we've hit the wall for catalytic techniques, or for the techniques involved in this just yet. Studying this question purely on its own terms, I think is pretty cool, and seeing how far you can push it.
Can you say more about some intuition about like why the conjecture is false?
This one?
Yeah, or like what the counterexamples are like.
There's a number of different subtle ways in which it could fail. In this case, it really, there's a great way to explain it. Well, yeah, you can reuse the space, certainly. I mean, I guess that's the long and short of it, right? Like this is false because it fails on its own terms. We said that Z should somehow come along for the ride and never come into play here, that somehow you can disconnect computing F from computing everything else that you already did before. And this just turns out to not, it just turns out that you can always use this in some way that, while it's completely uncorrelated with F, you look at F in a different light, you sort of tilt your head and turn it into something where any extra space can be used in a way that can be returned. But there's no great, I don't have a great answer for why it should fail here and succeed over there.
Or is this for some specific app?
No, this is this holds for every F. Because this tree evaluation problem, this result, regardless of which functions you plug into the intermediate nodes, you can get this.
Oh, thanks.
Yeah.
Did you ever collect the $100 associated with that conjecture?
Oh yeah, right. So Steve Cook, I want this to be known. Steve Cook owes me $50. He owes James $50 and he owes me $50. He also has probably paid for more things than I would really like to recall, so I could call it even, or just Erdish style, take the check and frame it on my wall. I'd be happy with those. But no, and Steve, if you're watching this, call me. Russell? I think this works.
Could there be some connection between this and the ZF problem and reversible computation? So it seems
For
like,
sure. I mean,
yeah.
everything we do to disprove this is reversible. I think the maybe more interesting question is, can you come up with ways to falsify the ZF conjecture that don't use reversible computation? We don't know of any techniques that don't. And if all we can do here is like stuff that works into the Z and then reverses it later in some predictable way, then there's a lot of, then this won't go so far. Like this can only, reusing space will only be so interesting. But for sure, reversible computation is a much bigger field than just this problem, and I don't think we've explored all those connections yet. Any other questions? Oh, Pavel?
Yes, I have a similar question, but instead of reversible, I would like to ask you about possible connection to catalytic computations.
Right. So this is, all right. So I actually worked on TEP twice before I came to Toronto. I just didn't take it very seriously. As an undergraduate, Michal Kuski visited Rutgers with this cool new paper called Catalytic Computing. And as you've all said, whatever the first paper you read is, you imprint onto it and you can't think about anything else for the rest of your life. So this, I'm glad that this happened, because otherwise I was never going to exercise this demon from my mind. But yes, catalytic computing is intimately involved in this. And that's why I said I want to know if there's more than reversible, because right now catalytic, all we can do is some amount of reversible stuff with space. And while that's all well and good, that means we'll never get beyond, say, polynomial time with catalytic log space, if this is for people who know what this is. But
for people who don't know what it is, could you define it?
all right, so imagine you have a hard drive and it's, sorry, this is, we all say this in our papers. So imagine you've got two work tapes, one which is very small, say log space, and one which is enormous, say poly size, but it's completely filled in, sort of in this exact ZF sense. If I give you that work tape, can you do anything more than log space is the question. And the answer is yes. You can get like non-deterministic log space and more. Do we know if it's in P? No, we don't. But if everything is, all you do is reversible, then yes, we'll do no better than
And the constraint is that you have to have.
and you have to reset it at the end. Yeah, like you can't just forget your answers up here. All right, I think we're running low on time. So if you have any other questions for the speaker, please take it offline.
Yes, thank you so much for the talk.